Welcome to our talk on using thermal analysis to characterize amorphous pharmaceutical materials. I'm Ann Newman and I'll be your presenter today. This talk is also how temperature can impact your amorphous materials, which is really important when we're talking about trying to develop these into drug products. Active pharmaceutical ingredients can be crystalline or amorphous, and we're going to be concentrating on amorphous today. When amorphous, they can be glassy or a powder, as shown up here. So this is from a melt, and this can be from any number of different manufacturing processes to form a powder. Now, amorphous APIs will not show the long-range order that you see in crystalline materials. So what you'll end up getting is a broad halo shown here versus very distinct peaks that you would see from crystalline materials. However, they do possess some short-range order, which can look something like this. And you can see that it's not as specific as a crystalline material. So it's more ordered than liquids or gases, but not as ordered as crystalline materials. So one of the issues we have with amorphous APIs is that they are significantly less physically and chemically stable than crystalline materials. They're a metastable state, so they want to thermodynamically go to the more stable state, which isn't a crystalline material. However, they do have higher apparent solubility and faster dissolution rate than crystalline materials, which is an advantage that we really want to exploit when we work with amorphous APIs. There are a number of amorphous systems that we use in the pharmaceutical industry that I'd like to describe. So the first one is amorphous API, where it consists only of API molecules, giving us the less ordered amorphous state. We can also have an amorphous salt, where we have proton transfer between an acid and a base, and the counterions can include a wide range of acids and bases that we all use for salt production. We can also have coamorphous, where we use similar counterions to salts, but we don't end up with proton transfer. So we end up using APIs, amino acids, counterions, sugars, a large variety of small molecules in order to produce miscible systems with amorphous API and amorphous small molecules. And we can end up with hydrogen bonding, pi-pi stacking. Usually there is never proton transfer, but we need to characterize it to make sure that we have a coamorphous and not the salt. So we have to make sure we can differentiate between that. Then we also have what are known as amorphous solid dispersions, where we have an amorphous drug usually with a polymer. And the polymer will stabilize this amorphous drug. And the way it does that is, here's our solid dispersion, here's our crystalline drug, and here's our plain amorphous drug. So it actually, when we have a solid dispersion, we have lower chemical potential, but we also have a much higher activation energy. So it's a lot harder to get over this activation energy in order to get to the crystalline material compared to the amorphous drug, which would have a lower activation energy. So when we have an amorphous solid dispersion, this results in better stability and higher dissolution, as we talked about before. This slide shows a number of amorphous multi-component systems, and I like to show this slide in order to illustrate the diversity of molecules we use in these multi-component systems. Sometimes we just end up with a small molecule, sometimes it's a second API. In amorphous solid dispersions we'll have at least one polymer, but there are a lot of more complicated systems that can end up with cyclodextrins, a second polymer, surfactants, phospholipids. So there's a lot of different possibilities with different solubilization mechanisms. Polymers and surfactants are going to maintain supersaturation differently than a cyclodextrin or a phospholipid would. So I always like to point out that no matter what amorphous system you have, water and solvent are going to change any properties that you have, and we're going to be talking about this a little bit more. But understand that there is complexity to multi-component systems, and sometimes you need these extra components. Sometimes a simple binary system will provide all of the properties that you need. So again, it's important that you understand what's out there, but you don't have to use it all the time. There are a number of amorphous products that are marketed, so this proves that we can produce amorphous materials that can provide the shelf life that we need in order to actually market a drug product with these materials. And when we go to amorphous solid dispersions, more than 20 products are on the market with amorphous solid dispersions, and this is just a small list of those that are available. So let's talk about the thermal aspects of amorphous materials. So amorphous solids can exist in two states, a supercooled liquid, also known as the rubbery state in the polymer literature, and this is a viscous equilibrium liquid form of the material. As we cool this material down, you can form a glass at lower temperatures, and this is a solid non-equilibrium form of the same material. So supercooled liquid is equilibrium, glass is not in equilibrium. Obviously, we usually use glasses for amorphous APIs because that is the form that is produced usually at room temperature, and that's where we are handling and developing our drugs. The temperature at which the supercooled liquid transforms to the glass is called the glass transition temperature, and this is a really important parameter whenever we talk about amorphous materials. There are a number of structural factors that can impact the glass transition temperature, including molecular size and shape, and this can be for the API or the polymer, and also the extent, strength, and direction of any hydrogen bonding, proton transfer, pi-pi stacking is all going to contribute to the glass transition temperature. Higher Tg usually results in better stability, but it also depends on what temperature we're storing the material at. That's just as important as the glass transition temperature. And these are commonly measured with differential scanning calorimetry, known as DSC, or modulated DSC. Energy temperature diagrams are a common way to associate the amorphous state, whether it be glassy or supercooled liquid, with the crystalline state. So at higher temperatures, we have the melt of a crystalline material, whether it be 1 or 2. And so this melt at high temperature, upon cooling, will end up as a supercooled liquid. This supercooled liquid will then transform into the glass at our glass transition temperature. We can also have an energy temperature diagram with volume, enthalpy, or entropy. And again, we have the same relationship with temperature. At high temperatures, we have the liquid. As we cool down, we have the supercooled liquid, and you can see that it's a little more ordered than what you see in the melt. And then as we go even lower below the glass transition temperature, we transform into the glass. So we have the melt to the supercooled liquid to the glass, and you can see that more order is observed as we go to lower temperatures. A couple of other parameters that we need to discuss when we talk about amorphous materials are mobility and viscosity and how they relate to stability. So molecular mobility is the ability of the molecules in an amorphous material to move. So we all consider these as static systems, but they're really not. These side chains and various functional groups are still moving around in the amorphous state. So if we have more movement, there's a greater possibility for crystallization and or degradation. So viscosity of the amorphous material can also slow down crystallization. If you think about a very viscous solid, it's going to be harder for the molecules to move and crystallize, and that's at lower temperature. At higher temperatures, you're going to have a less viscous liquid, and it's going to be a whole lot easier for the molecules to move around and crystallize. So these two parameters obviously change with temperature. So the liquids exhibit short relaxation times and lower viscosities, and glasses exhibit longer relaxations and higher viscosities when they're at lower temperatures. So for stability, we want low molecular mobility and higher viscosity that's found in the glasses. And again, because we're working at room temperature, we need to measure these at the temperature that we're going to be using them at. So we got less mobility, less movement, less chance of crystallization and degradation, depending on what our mobility and our viscosity numbers are. Now, if we want 3-year storage for shelf life, we want molecular mobility around 10 to the 8th seconds. So we need to store below Tg in order to obtain this particular mobility in order to maintain shelf life. So let's talk a little bit more about molecular mobility in glasses. So this is a really interesting diagram that relates temperature and the different phases that we're going to see at these temperatures with stability, specifically crystal nucleation and crystal growth. So when we talk about molecular mobility, there are primary relaxations, which are also called alpha relaxations. These are slow, they're cooperative diffusions. Think about it as translation and rotational motion of whole molecules or polymer segments. And this results in the Tg that we commonly report. It's also known as Tg alpha. So again, here we have our melting point, As we cool down, we have our Tg alpha, and this is again where a supercooled liquid is going to transfer to our glass. So what we want to do is we want to slow this down, and common practice tells us that if we want to slow it down to a few years, if we store somewhere at Tg minus 50, hopefully we're going to reduce nucleation to the point where we will have minimal crystallization and we can get shelf life for whatever it is, 3 years. So it slows down the nucleation and the subsequent growth. So as we move down to lower temperatures, we have secondary relaxations, which are called beta relaxations or Johari-Goldstein, JG reactions. And they're faster and they're not cooperative local motions. So they're associated with very individual molecules, polymer main chain segments, as well as their side chains. And they're very hindered rotational motions. So these are the precursor to primary alpha relaxations. Now, if we want minimal motion, then we want to store things at Tg minus 100. If we store at Tg minus 100, that's an indication of what we call Tg beta. And Tg beta at this temperature will prevent nucleation from occurring. So if we have no nucleation, then we're not going to have any crystal growth as we continue to higher temperatures. And this is the goal when it comes to stability. So from the last slide, we understand what mobility we want to target, the viscosity, but here's a much simpler way of looking at it. Is there a temperature where I can store this, where I will either minimize nucleation, or can I prevent it significantly at a lower temperature? Now I want to talk a little bit more about glasses themselves and also the glass transition temperature and what things may change both of these properties. So depending on your thermal history, a glass can form with slightly different energies, and this comes from a supercooled liquid. If you decide to produce the glass one way, you could end up with glass 1. If you decide to produce it a different way, you could end up with glass 2, and they can have slightly different free volumes, slightly different temperatures. And you can see again where they split off, you are going to get a different glass transition temperature. And these are different kinetic phases of the glass. This is not polyamorphism, that's an entirely different phenomenon. This is just a kinetic form of the glass, but they are very real and they will occur during development. And they can result in variable properties, and this can include different glass transition temperatures, it can include different moisture uptake, it can include different stabilities depending on how different these kinetic glasses are. So again, understanding how you're producing your amorphous material and relating it back to various properties can be very, very important during drug development. So to continue on this theme, different preparation methods will produce different glasses. And here we have a number of different preparation methods that commonly produce amorphous materials. And sometimes the intermediate will be through a supercooled liquid. And you can have slow cooling or fast cooling, and both of these can produce very different kinetic glasses. If you go through the glass, which would be below your glass transition temperature, then you can end up with different storage conditions, different handling conditions, which again can give you significantly different glasses. Now, some of these conditions are the cooling rate, it can be the storage temperature, it can be the storage RH. All of these can produce the different glasses when you're manufacturing amorphous materials. Tg is also dependent on the rate of cooling from the supercooled liquid. So if you decide to do a rapid cool, you will end up with a higher Tg. If you decide to do a slow cool, you will end up with a lower glass transition temperature. And this thermal history, as we call it, will directly impact the Tg value obtained. So if you start getting variable glass transition temperatures, it could be that you're using different methods or you're storing them under different conditions, which is giving you different kinetic glasses. So amorphous materials can also change just by sitting around over time, and this is called aging or relaxing. So we're actually going from one kinetic state down to another kinetic state, which is actually a little bit more stable for the amorphous material. Now the DSC will go from your very pretty glass transition temperature to what's known as an enthalpic relaxation endotherm. And a lot of times people look at these minor endotherms and say, what in the world is this? What happened to my glass? It's still there. It just relaxed from one state to another, and that extra energy is this minor endotherm. So upon relaxation, what's actually happening is we're going from a less dense, unaged amorphous matrix. And then we end up, once we age it, we end up with a higher density and a lower free volume, which ends up making it more stable. So relaxation can actually change the properties of the amorphous material, including TG, moisture uptake, a number of things that we normally measure for an amorphous material. Again, longer aging times will result in larger enthalpy relaxation, so you can see that this will grow over time depending on your conditions. This one happens to be at 61 degrees, but you could see something similar even at room temperature over days, weeks, or months. So if you start seeing an increase in the enthalpic relaxation in your DSC, it means that you're converting from one kinetic glass to another. We mentioned earlier that other components can be part of amorphous materials, and this can include water and solvents or even polymers. So let's talk about water and solvents first. These can act as plasticizers, which lowers the glass transition temperature of amorphous materials. For example, water has a TG of -137. So when you combine that with the TG of our amorphous API, you can see that the temperature is going to decrease significantly as we increase the amount of water. And this is an example with the indomethacin, where you have the glass transition temperature versus the weight fraction of water. And you can see where the glass is versus the supercooled liquid. And as we add more water, we end up moving into the supercooled liquid, which has greater mobility, which means it's going to be less stable. There's just a rule of thumb, it's an estimate only, that about 1% water will decrease the TG about 10 degrees. That's a lot. So again, when you look at your water content or your solvent content, understand what the impact could be on your glass transition temperature and your stability. So as I said, polymers and other molecules can also be added to our amorphous solid dispersions, and we do that because they act as anti-plasticizers, which actually raise the TG of amorphous materials. So if I have an amorphous API that has a TG around 40 and I want to raise that, I can find a polymer that has a TG significantly higher, maybe 90 or 100, and hopefully I can raise that glass transition temperature of the amorphous solid dispersion in order to get it to the point where I have a much higher glass transition temperature, as you see here for indomethacin and amorphous. Again, here's our glass transition temperature. Here's our weight fraction of PVP. We start out with indomethacin, amorphous indomethacin TG around 47. If we add even 80% polymer, I can get a TG of about 150. That's significant from a stability point of view. So this is one of the reasons we add polymers and other materials in order to try and raise the glass transition temperature. So we can actually estimate this. The easiest way to do this is the Fox equation, and it's really just the weight fraction of whatever you're going to put in there. It can be water, it can be polymer, with the glass transition temperature of that component. And it's a very simple mathematical equation, and here's an example. If you have 5% water and you have a TG of about 50 degrees for your amorphous API, we have 5% water with a glass transition temperature of 135 K plus 95% of our API with a TG around 323, and that gives us a TG mix of about 29 degrees. So again, a very simple equation just to give us an estimate. So as we saw on the previous slide, the TG of multi-component systems does change with composition. And we can have positive or negative deviations to our theory. And for the theory, we can use the Fox equation, which we saw on the previous slide. You can also use Gordon-Taylor or Couchman-Cross. So sometimes you end up with a negative deviation from theory. So here we have the calculated straight line, and here are experimental points, which are actually lower than what we calculate. And this is due to the net free volume change, and this is positive due to non-ideal mixing. And also sometimes we can have weaker interactions which will cause our TGs to be lower than predicted. We can also have a positive deviation where we have higher TGs than predicted. This is due to, again, the net free volume change is negative due to non-ideal mixing, and we may have stronger interactions. So if you calculate your estimated glass transition temperature, but the experimental is not right on, you might want to do a number of different weight fractions in order to see if you've got a positive or negative deviation from the theory. Another consideration for multi-component amorphous systems such as solid dispersions and coamorphous materials is miscibility. And this occurs when one phase is produced in a multi-component system. So there's actually interactions between the molecules, there's a favorable net free volume change, and they actually act as one phase. Miscible systems usually exhibit one glass transition temperature. So here we have indomethacin and citric acid, and here we have a miscible 1 glass transition temperature when you have 0.1 citric acid in the system. However, when you increase this to 0.5, you end up with 2 glass transition temperatures, and this is an immiscible system, or this is a physical mixture of the amorphous API and, in this case, the amorphous citric acid. So each TG is representative of the individual amorphous phase. But it's also important to understand that not all systems are miscible or immiscible along the entire range. Sometimes you can have miscibility over some concentrations and immiscibility, shown by these 2 glass transition temperatures, at higher or lower concentrations. So again, not all systems are miscible over the entire range, so it's important for you to understand if you're going to be miscible or immiscible in the targeted concentrations that you're going to use. Now, immiscible systems may also exhibit 1 glass transition temperature, and this is a limitation of the size domains that the DSC can actually see. Other techniques are needed to confirm the miscibility or immiscibility that you may see with the DSC. So spectroscopic techniques such as IR, Raman, solid state NMR can also provide information on miscibility. Here are a couple of example systems where we actually saw 1 glass transition temperature. However, there were other techniques that demonstrated that these systems were immiscible and were actually physical mixtures. So immiscible systems will tend to crystallize faster than miscible systems, which is another reason that you really want to understand, is it miscible and hopefully more stable, or is it immiscible and probably less stable? Molecular properties can also play a role when we're talking about glass transition temperatures. For example, different grades of polymers can give very different glass transition temperatures. Here's an example with PVP, different grades of PVP, K90 ranging from a molecular weight of 1500 K all the way down to K12, which has a molecular weight of about 2K. And you can see that the glass transition temperature ranges from 177 all the way down to 101, which is significant. Even if we look at different polymers with a similar molecular weight, we can see a significant difference in glass transition temperature. So it's not just due to the molecular weight, it can also be due to the interactions, the different hydrogen bonding, conformations. All of those things will play a role in the glass transition temperature. So here we have 50K PVP K30 with a glass transition temperature of 156, but if you go to PVPVA, it drops to 102. So again, understanding how your glass transitions change with molecular weight can also be very useful. If you decide to make amorphous dispersions with different salts and the counter ion that you use can also impact the glass transition temperature. Here's an example with indomethacin where small inorganic counter ions will give you a much higher glass transition temperature, around 140, versus the larger inorganic counter ions, which don't increase your glass transition temperature much. Amorphous indomethacin is about 46, 47, and this is raising it to about 60, 65. So it is an increase, but it's not as much as you would get with a different counter ion. Let's talk a little bit more about how to measure glass transition temperatures. A variety of methods have been used to collect glass transition temperatures, as shown here. The most common methods, especially the ones we've been talking about, are differential scanning calorimetry, modulated, and dielectric analysis. But again, as we've talked about, there are a lot of variations in the sample that can cause TG differences. But also, analysis parameters can impact the measurement as well. And so we're going to talk a little bit about that, whether it be the water solvent content, pan configuration, ramp rate, and even the modulation period and modulated can impact the value that we end up getting. There are a number of different pan configurations we can use when we're doing DSC analysis, and these include open pan, closed pan, hermetically sealed pans, closed pans with a pinhole, crimped pans, lots of different choices. When we talk about pan configuration and glass transition temperature, we need to understand how the pan configuration is going to impact our measurement. So if we want a wet glass transition temperature, we want to know the effect of the water or the solvent on the glass transition temperature. As we said, this will decrease our TG significantly. So we want to use a hermetically sealed pan, no pinhole, because we want to prevent volatilization. We don't want any of that water or solvent leaving the pan. Now, if you end up using a crimped or a pinhole pan, this will allow for volatilization and will not provide the wet TG. We should also report the water content whenever we're looking at or measuring wet TG values. So here with citric acid, we have a difference between a dry TG and a wet TG of about 40 degrees. That's significant. That is a huge difference in glass transition temperature when we're talking about stability. So for a dry TG, we want to remove all the solvent and thermal history, so we use an open pan so everything can leave. We can use a DSC cycling experiment in order to do this as well, but note that dry TG values represent the best case scenario. They will give you the highest glass transition temperature that's available. However, under normal handling conditions, we're probably somewhere down here. So we have a significantly lower glass transition temperature. So when you're collecting your DSC measurements, understand and measure both. Measure your wet TG and your dry TG, but also understand how your wet TG changes with the amount of water you have in the system. So TG is also going to be dependent on the rate of heating in your DSC. So your ramp rate is very important. So faster ramp rates, your TG will be higher. And if you have a slower ramp rate, your TG is going to be lower. You're also going to see an increase in signal, and you're also going to see an increase in enthalpy relaxation. So again, understand what type of data you're trying to get out of your DSC system. When comparing TG values, always use the same conditions to make them directly comparable. Multi-component systems showing 1 TG, the width of the glass transition temperature can also give you information about miscibility. So a wider glass transition temperature indicates less miscibility, but the width will also impact the TG reported. Some people report onset, some people report midpoint. And if you have a glass transition temperature which is very wide, your onset and your midpoint can be very, very different. So understand the impact of the width of your glass transition temperature and make sure you always delineate if you're talking about the onset or the midpoint measurement when you're reporting it. So to summarize, amorphous materials can be moving targets, and hopefully you also realize that the TG values that we're trying to measure are dependent on a lot of different parameters, all of these included on the screen. And we need to understand what our TG value represents, how it may change, and conditions that are needed to maintain the amorphous material. So while amorphous materials are difficult to develop, it doesn't mean that they can't be developed. We just have to have a different understanding of what our conditions are. So we need to try and increase the stability, and we've talked about how to do that. We need to determine storage and handling conditions in order to determine where it is happy, where it is stable, where it will stay amorphous. And we also need to collect additional data sometimes to estimate that stability. We can look at miscibility by various methods and also molecular mobility by various methods. So again, it's not that we can't develop amorphous materials, we just need to collect different data and look at it in different ways in order to make sure that we have the stability and shelf life that we need. So thank you for your attention, and I hope you enjoyed the talk.